In this section, we're going to continue the idea of hypothesis testing for our population mean, but in this case, when we do not know what our population standard deviation is. If you remember from 8.2, we knew what this value was, this population standard deviation. But in this case, what happens if you don't know this value? So that means you have to replace it with something like a sample standard deviation. And we know that that's going to follow a new distribution, a student t distribution. And all of this should sound familiar because it's something that we kind of done with confidence intervals. Remember when we have the case when confidence intervals, when we know what our population standard deviation is, when we don't know, and with proportion. So in this section, 8.3, we're going to go over some more hypothesis testing when population standard deviation is unknown. Okay, so there's two ways to perform hypothesis testing. There's the critical value method and there's the p-value method. But in this case, when our population standard deviation is unknown, the p-value method actually becomes a lot more difficult if you don't have access to a very fancy calculator or a fancy computer. So for this class, we're not gonna deal with p-value method. We're only going to focus on the critical value method because in that case, we only have to use is the chart, the little table, and no fancy calculator. Okay, so all this should be review, but if we recall what a student t distribution is, when we do not know our population standard deviation sigma, then we could use the sample standard deviation s to estimate the population standard deviation sigma. And if you recall, this should be a reminder that this is the formula for a sample standard deviation. But we already had a lot of practice computing this in section 3.2, I believe. Yeah. So if you still have question about computing your sample standard deviation, you should go review that section. Okay, so when we use S to estimate sigma, the sample distribution for our sample mean follows a new distribution called the student t distribution. And the number of degrees of freedom for the student t distribution is one less than the sample size, or n minus 1. And again, this all should be review. Okay, so from 8.2, we talked about a test statistic. In this case, when we do not know our population standard deviation, we still need to compute a test statistic, but it's going to look a little bit different. So here, in the case that sigma is unknown, we compute our test statistic, and often this is called the t-test or the t statistic, and it's going to be x bar minus mu naught divided by s over square root of n. So all we did is replace sigma with our sample standard deviation s. And one thing you want to note, so note here, is that the t statistic, this has a student t distribution with n minus 1 degrees of freedom. So what does that mean? That means that we are able to use the chart to compute critical values. Okay, critical regions and significant levels. So it's basically the same idea, but with the student t distribution. So here, the critical value for a student t distribution forms a boundary between the values that are considered unusual and the values that are not. The region that contains the unusual values is called the critical region. The significant levels, there's two definitions of it, but they're both saying the same thing. It's the probability that we use to determine whether an event is unusual. It's called the significance level of the test. And again, it's denoted by the letter alpha. So this is just a Greek letter. And the way to write it is like this. Okay. The significance level alpha is the area of the critical region. And depending on which test you're dealing with, either a left tail, right tail, or two tail, your critical value and your critical region is going to look a little bit different. So here, let me divide the cases. When we're dealing with a left tail test, and again, when we know this is a left tail test because our alternative hypothesis mu is less than mu naught, and this means that it's a left tail test. So our critical value is going to be denoted as negative t of alpha. And the area to the left of this value is going to be alpha. So let me just write a couple things down. For left tail h sub 1, the critical value is negative t of alpha. So this is just our critical value, which has area alpha to its left. And then this is important. We reject our null hypothesis h sub 0 if your t statistic or t test is less than or equal to negative t of alpha, your critical value. And again, this is the case when we're dealing with a left tail test. Okay, how about a right tail test? Then your critical value will be positive t of alpha, where the area to the right of this will be equal to alpha. So just a couple things I want to write down. For right tail h sub 1, the critical value is t of alpha. So this is our critical value when we're dealing with, right tail tests, which has area alpha to its right. And this is important. We reject our null hypothesis if t, this is our test statistic, or our t test, or in other words, our t statistic is greater than or equal to t of alpha, where t of alpha is just our critical value. Okay. So what happens when we're dealing with a two-tailed test? Well, then our critical values will be negative of this value here and positive of this value here, where if we add the area to the left and to the right of these, they're going to be equal to alpha. So here, for two-tailed h sub 1, the critical values are t of alpha over 2, which has area alpha over 2 to its right, and we negative t of alpha over 2, which has area alpha over 2 to its left. So in the case of a two-tailed test, our critical values, well, we have two, will be negative t of alpha over 2 and positive t of alpha over 2. Then, and this is important, we reject our null hypothesis if t, or if our t statistic, or our t-test, is greater than or equal to t of alpha over 2, or t, or t-test, or t-statistic, is less than or equal to negative t of alpha over 2. So if one of these satisfied, then we reject our null hypothesis. Awesome. So now you're probably asking, how do we find these critical value? How do I find these negative t of alpha, positive t of alpha, and negative t of alpha over 2 and positive t of alpha over 2? How do I actually find these values? Well, we're going to do some practice of how to find these values. Okay, example 1. Find the critical values, or values, for the following values of significant levels alpha, our sample size n, and our alternative hypothesis h sub 1. Okay, so here we want to find the critical values with, if your significant level alpha is 0.05 and your sample size is 3, and your alternative hypothesis is mu is greater than mu naught, where mu naught, again, is just a number, it's a value. So first thing we want to know, are we dealing with a left tail test, a right tail test, or a two tail test? Well, again, if this is greater than, it kind of looks like an arrow pointing to the right. So that kind of gives you an idea, like, oh, we're dealing with a right tail test. So this is a right tail test. Awesome. And this is going to help us how to find the critical values. Because if you look up here, if we have a right tail test, then we're looking for the critical value positive t of alpha. All right. So first thing we want to know is we want to compute our degrees of freedom. The degrees of freedom. And I'm just going to call it df. And again, this is just n minus 1. Here n is 3, so it'll be 3 minus 1, which is equal to 2. Nice. So we want to find t of alpha. And since we know what our significant level is, our alpha, since it's 0.05, we could just say we're trying to find t of 0.05. We want to know what this value is. Well, we have to look back into our table. If you remember this table, this is just table A3, the critical value for student t distribution. We want to look first the degree of freedom. Since here we have a degree of freedom of 2, we have to look at the row of 2, which is right here, because this is our degrees of freedom. The only difference is that we're trying to find this value here, 0.05, which is somewhere up here. So this is the value of this here, alpha. Or in this case, the value here, 0.05. So if we look at here, this is 0.05. So I would highlight this whole column. Where they intersect here, this is going to be our critical value. So it's 2.920. So here, t of alpha, or t of 0.05, is equal to 2.920. And let me just box this in. And again, I got this value from this table here. Okay. What happens if we have a significant level of 0.01 and we have a sample size of 26 and our alternative hypothesis is mu not equal to mu naught. And again, mu naught is just a number. First, we want to ask ourselves, are we dealing with a left tail test, a right tail test, or a two-tail test? Since this is not equal to, we know that we're dealing with a two-tail test. So this is a two-tail test. And that kind of helps us out, because if you look up here, if we're dealing with a two-tail test, and we are, then we're going to have two critical values. One is going to be negative t of alpha over 2, and the other one is going to be positive of t of alpha over 2. So that's what we're trying to find. Okay, first we want to do is actually compute our degrees of freedom. And I just call it df for degrees of freedom. And we know this is n minus 1, which is 26 minus 1, which is 25. Okay, so just a reminder, we want to find t of alpha over 2. Let me just put it here. Negative t of alpha over 2 and positive t of alpha over 2. Since we know what our alpha is, our significant level, we have a significant level of 0.01. What we could do is just plug in that value there. So this is going to be equal to negative t of 0.01 divided by 2. And this is also going to be equal to t of 0.01 divided by 2. And then this will be negative t of 0.005. And this will be positive 0.005. Because 0.01 divided by 2 is 0.05. Okay. Now we're able to use the table. So just a reminder that our degrees of freedom is 25. So what we have to do is look for the number 25 here in our degrees of freedom, which is right there. And since we're working with alpha over 2, which is 0.005, we have to look up at where 0.05 is, which is right here. So we have to highlight that column. And where they intersect is going to be our critical value. So this is 2.787. So here, this will be 2.787, and this will be just the negative value of this. So this will be negative 2.787. So let me just box this in. So we found our critical values. Awesome. How about this one? We want to find the critical value with a significant level of 0.10, a sample size of 81, and a alternative hypothesis of mu is less than mu naught. Since we want to know what tests are we working with, is this a left tail test, a right tail test, or a two tail test? Since this is less than, it kind of looks like there's an arrow pointing to the left. So you kind of know that, oh, this is a left tail test. Okay, and that kind of gives you an idea, because if you look up here, a left tail test, we're looking for the critical value negative t of alpha. So this will be, okay, so first thing is compute the degrees of freedom. df, which is n minus 1, which is 81 minus 1, which is 80. So now we want to compute negative t of alpha. Since we know what our alpha is, since it's 0.10, we could say that we're looking for negative t of 0.10. So how do we find this value? Again, we have to use the table. So our degrees of freedom is 80. So using the table, we have to look for 80, which is right here, because this is our degrees of freedom. And we're working with an alpha of 0.10. So you have to look up and look where 0.10 is, which is right here. Then we have to know where they intersect, and they intersect right here. So this means that our critical value is 1.292. But since we're working with a left tail test, this is going to be the negative version of that. So this will be negative 1.292. Great. Last one. So what happens when we have a significant level of 0.05, a degrees of freedom of 14, and a alternative hypothesis of mu not equal to mu naught? So what you have to do is figure out, are we dealing with a left tail, right tail, or two tail test? Since this is not equal to mu naught, we know that this is going to be a two-tail test. Two-tail test. So first thing you want to do is compute our degrees of freedom. I just call it df for degrees of freedom. And this is going to be equal to n minus 1, which is 14 minus 1, which is equal to 13. Since we're dealing with a two-tail test, if you look up here, we have to find two critical values, negative t of alpha over 2 and positive t of alpha over 2. So we're looking for negative t of alpha over 2 and positive t of alpha over 2. Since we know what our alpha is, what our significant level is, it's 0.05, we could just plug it in. So you could say that we're looking for negative t of 0.05 divided by 2. And let me just move this. Positive t of 0.05 divided by 2. Or you could say this is negative t of 0.025 and positive t of 0.025, because 0.05 divided by 2 is 0.025. We want to find what these values are. So if you look at our degrees of freedom, which is 13, we could use the table and find where that degree of freedom is. In this case, it's right here, 13. And then we know we're dealing with 0.25. So we look at that number up here, which is right here. So we have to highlight that column, and then where they intersect, it's going to be our critical value. So 2.160. So here, our critical value is going to be 2.160. And this would be the negative version of that number, or negative 2.160. Now that we did some example of how to compute our critical values when we don't know what our population standard deviation is, we're able to actually talk about some of the procedures of performing hypothesis testing. And again, without knowing what our population standard deviation is. So before we begin, again, we have to check some of the requirements. If one of these do not satisfy, then we're unable to perform hypothesis testing. So we have to obtain a simple random sample of size n. We have to compute our sample mean, x bar, and our sample standard deviation, s. And again, the reason why we have to compute, or it's given to us, our sample standard deviation is because we're in the case when we don't know what our population standard deviation is, which is sigma. Our sample mean distribution is normal, and you could check this by checking one of two things. If x comes from a normal distribution, or the population is approximately normal, this should state somewhere in the problem. If it doesn't, then if your sample size n is greater than 30, then you could assume that our sample mean distribution is approximately normal. Once all of these are satisfied, then we're able to proceed to compute hypothesis testing. Okay, so performing a hypothesis test for our population mean when sigma is unknown using the critical value method. So it's kind of the same idea for the previous section. We want to state the null and alternative hypothesis. So the null hypothesis is in this form, and our alternative hypothesis is one of these three forms. Second, we want to find the number of degrees of freedom, and this is just n minus 1, and the critical value corresponding to the desired significant level, alpha. And again, we did a lot of practice how to compute our critical value here. Then we want to compute the t-statistic, also called the t-test, which is this formula here. Notice that we only replace sigma with s, because that's the idea here. Then we want to determine whether we reject our null hypothesis or not. So how do we know this? How do we know when to reject our null hypothesis? Well, it kind of depends of what test you're dealing with. If it's a left tail test, and we know this is left tail because mu is less than mu naught, then we reject it. We reject our null hypothesis if our t-statistic is less than or equal to negative t of alpha. And again, negative t of alpha is just our critical value. If we're dealing with a right tail test, and that's when our alternative hypothesis is mu is greater than mu naught, then we reject our null hypothesis if our t-statistic is greater than t alpha. And again, t alpha is just our critical value. If we're dealing with a two-tailed test, then our alternative hypothesis mu is not equal to mu naught, and we reject our null hypothesis if our t-statistic or our t-test is greater than t of alpha over 2, or our t is less than or equal to negative t of alpha over 2. And then step 5, we state our conclusion. And it's kind of the same way as what we did earlier. If we reject the null hypothesis, we could say that we have sufficient evidence to conclude, and then kind of state your alternative hypothesis. If we fail to reject our null hypothesis, then we could say like there is not enough evidence to conclude, and then you kind of state your alternative hypothesis. So let's do an example. The market research firm Salary.com reported that the mean annual earning of all family practitioners in the United States was $178,258. Here, a random sample of 55 practitioners in LA and Los Angeles that month had a mean earning of $192,340 with a standard deviation of 42,387. do the data, so we want to know, do the data provide sufficient evidence to conclude that the mean salary for family practitioners in LA is greater than the national average? So the first thing I want to do is actually collect all the things that I know, like all the information that I'm given. So the easiest one will be the random sample of 55 family. So this will be, our sample size will be n is equal to 55. And in this sample, they were calculating the monthly mean earning, which is $192,340. So here, X bar is equal to 192,340. And since this is a sample, and they say they computed its standard deviation, this is going to be the sample standard deviation, S, which is 42,387. So S is equal to 42,387. Nice. Oh, I forgot to mention, we're dealing with a significant level, alpha. Let's say it's 0.05. So we have a significant level, alpha, to 0.05. Nice. We want to check the requirements. Since our sample size n is 55, which is greater than 30, then we could assume that our sample mean distribution is about normal. Okay, so now we want to establish the null and alternative hypothesis. So we want to find our null hypothesis, which is mu is equal to some value, and our alternative hypothesis, which is mu is either less than, greater than, or not equal to some value. So how do we figure this out? Well, we have to read the question very easily, or very carefully. Here, it's saying that, do the data provide sufficient evidence that to conclude that the mean salary for family practitioners in LA is greater than the national average? And we were given that the national average was 178,258. So here our alternative hypothesis is that this is greater than 178,258. So this will be equal to 178,258. So our null hypothesis is saying that the average of family practitioner in LA is equal to this value. But the alternative hypothesis, the other argument, is saying that the mean earning of family practitioner in LA is actually greater than this number. So that's what it's stating. Also, are we dealing with a left tail, right tail, or two tail test? Well, since it's greater than, it kind of looks like there's an arrow pointing to the right. So we know that this is a right tail test. So this is a right tail test. Cool. So what I like to do is actually write down our null and alternative hypothesis, so that way it'll be a little bit easier when we state our conclusion. So our null hypothesis stating that the mean salary for family practitioners in LA is $178,258. But the alternative hypothesis saying that the mean salary for family practitioners in LA is greater than $178,258. So these are the two. So this is the null hypothesis and this is the alternative hypothesis and what they're stating. Now we want to find the critical region and critical value. Forgot to add that part. So since we're dealing with a right tail test, so that means, let me just draw this real quick. Standard normal curve would mean 0. Since we're dealing with a right tail test, then we have to find this value, critical value, z of alpha, and this will be its critical region. Oh, sorry, not z, since we're doing t of alpha. Right, there we go. Since we don't know our standard deviation, our population standard deviation. So it's t of alpha. So first thing we have to do is compute its degrees of freedom, df, because sigma is not known. So this will be n minus 1, which is 55 minus 1, which is equal to 54. Okay, so just a reminder, we need to find the value, our critical value, t of alpha. Since we know what our significant level alpha is, it's 0.05, we could say that we're trying to find t of 0.05. And then we could use the table. So we have a degrees of freedom of 54. So what we have to do is look at degrees of freedom, find where 54 is. Notice that 54 is not in our table. So remember, we have to find a number that's less than 54. In this case is 50. And we're working with alpha equals 0.05. So then that will be right here, 0.05. And we want to find where they intersect. And they intersect right here. So that means this is our critical value. So this be equal to 1.676. Nice. So we just found our critical value, and this whole thing, this area, is our critical region. Okay. What is the value of our test statistic, or our, another way of saying it, what is our t statistic? So remember that t is equal to x bar minus mu naught divided by s over square root of n. Since we know all of these values, all we have to do is just plug them in. So this is going to be equal to 192,340 minus 178,258 divided by 42,387 over the square root of 55. And if you put this in your calculator, this should be equal to 2.4638 or 2.464. Now we want to state our conclusion. We want to decide whether we reject or fail to reject our null hypothesis. So how do we actually do this? Well, since we're dealing with a right tail test, remember that here a right tail test, we reject if our t statistic is greater than our critical value t of alpha. So here we want to ask a question. So question, is our t statistic greater than or equal to our critical value t of alpha? Question mark. So this is saying, is 2.464, this is our t statistic that we just computed here, is this less than, is this greater than or equal to 1.676, and this is just our critical value. Is this true? And the answer is yes. It is, because 2.464 is a bigger number than 1.676. So we could say that since t is greater than or equal to t of alpha, we reject the null hypothesis. Yay. We reject it. Oh, I guess another way you could say it is that thus we reject our H naught. Cool. Last thing. We want to interpret our result. It doesn't really matter if we did this, if we can actually explain it in words. So since we reject our H naught, if you look up here, we could say that we have sufficient evidence to conclude and whatever our alternative hypothesis was. So here we could say that we have sufficient evidence to conclude that, and what was our alternative hypothesis? It was that the mean salary for a family practitioner in LA is greater than this number. So what we do is just copy and paste. So we could say that we have sufficient evidence to conclude that the mean salary for a family practitioner in LA is greater than $178,258.